Okay, so while you're coming in, remember you guys owe us a problem set today. You're supposed to turn it in. I'd like them at the beginning of class, but we're going to lecture for the first hour today. So at the end of that lecture, turn them in, and then we're going to have a problem session afterwards where Bonert will go over the problems. And then as promised, there's another homework assignment. It's a mixture of problems out of Lilly and other sources. So I posted this lecture already. You can write this down if you want. There are 3 more problems out of chapter 1 in Lilly, and then there are actually 3 more problems written here. And then one of them is a little exercise where after today we're going to finish up the discussion of quantum mechanics, and we're going to go on to talking about radioactivity. And one of the things I'd like you to do is to go to a website that we set up several years ago where there's a bunch of radioactive decay data that we actually took. And the idea is to use that data to extract the half-life of an isotope from real experimental data. And when you go to this website, there's a set of instructions there on how to analyze that data. If you have questions, come see me or come talk to the TAs, but hopefully it's self-explanatory about how to analyze the data, extract the half-life from that data, and then compare your result to what the real half-life, the known half-life of the isotope is by going online and looking up that value. And so these are websites which I'm going to refer to over and over again throughout the year, and I'd like you to get familiar with them because they're enormous sources of nuclear data. Okay? So that homework assignment will be due next Friday. And yeah, I know there's a short week. I know there's a holiday on Monday, but nevertheless, we're going to plow ahead here. Okay, so we've been talking about quantum mechanical tunneling and this idea that even though classically things can't penetrate barriers, quantum mechanics says it actually happens. We have a little demonstration to illustrate this idea. It's not a perfect analogy. It's not exactly what's going on, but it illustrates the basic principle. So the is a phenomenon that hopefully you're familiar with from optics, which is that of total internal reflection. So if I have a light source that's incident on a prism like that, and I arrange things so that the photons go in at a certain angle, they will reflect off that inclined surface and totally internally reflected, meaning that no light will be transmitted through the inclined face of that prism. So on the other side, I won't see any light. However, it turns out the light wave actually does propagate a little bit beyond the edge of the prism. It's called an effervescent wave. And so if I bring another prism nearby and I make the separation not too great, then this wave can actually travel across the gap there and through the second prism, and then I actually see light over here. So it's kind of like the light tunneling through that gap, very much like the alpha particle tunneling through that barrier we were talking about the other day. And this can happen as long as the gap isn't too big. And you might say, well, what's too big? And the thing that determines the size that's permissible is the wavelength of the light, okay? So we're going to do this demonstration with microwaves, not with light, but microwaves are just another type of photon, and the wavelength of the microwaves that this generator produces is about 3 centimeters. So I'm going to turn this on. So one is a emitter of microwaves, the other is a receiver. And in a second, when this warms up, you're going to hear a noise, which is the receiver hearing the microwaves. There we go. Okay. So when I've got the transmitter on and the receiver line, and if I move it away, okay, the microwaves are traveling in a straight line. The receiver doesn't hear them anymore. You don't hear anything. Okay. So I put that back over there. Try not to knock it off. Here's my prism. Okay, so this is the first prism. Paraffin blocks. And now you don't hear anything because the microwaves are getting totally internally reflected. And if I bring the horn over here, I hear it. So the microwaves are coming in, bouncing off this surface, and coming out this way. Okay? And you don't hear anything. And now I bring a second block up. And hopefully I can do this without knocking things off the table. And isn't too big, and you can hear it again. Okay? So now what's happening is the waves are coming through here. Almost all of them are getting reflected over here. But there's a small probability the wave is transmitted across that little gap, which you can't see, but it's probably a centimeter right here. And then they get into this block and they're transmitted through. So the light, in a sense, is quantum mechanically tunneling across that gap. Now, actually, this is predicted classically. It isn't really quantum mechanics that's happening here, but it's an analog to what we're seeing in quantum mechanics. Okay? Okay. Turns out you can actually do this with visible light. I've tried doing it. The trouble is you need... I haven't been able to do it yet, but you can do it with visible light. You get two prisms, you bring them together, and you'll see the light going through when you get the separation just right, but it has to be really, really small. How are we doing? Okay, so I will get this out of the way, and then we'll go on with the rest of the lecture. Yes?
Does that decrease whenever you cause the tunneling?
Yes, so thank you. So the question is, what happens to the intensity there? And the way I would quantify that is if I move the blocks further and further apart, the probability for that tunneling goes down exponentially with the separation. Just like the probability for the tunneling through that barrier we talked about the other day goes down exponentially. So this effervescent wave propagates out a little bit, but it's falling.
I meant if you look at the intensity of the waves that you're receiving that are reflected.
Over here?
Yes.
Yes.
So that would decrease if you moved in the second prism.
Not noticeably, because there's such little intensity coming out this side anyway. We can do the experiment if you want. I don't think it makes any difference. Let's check. These are old tube devices, so it takes a little while to warm up. Get this out of the way. Oh, if I turn the other, helps if I turn that. Okay. Put this over here. Okay. And I listen over here, and then you want me to bring this block up and see what happens. Okay. Not really. The probability of it coming out the side is so small, it doesn't make any difference whether the other block is there. Okay. Just turn that off and get out of there. Okay. So I keep saying that alpha decay is an example of this, and we're going to come back to this over and over again. For the first time, we calculate the probability of tunneling through a barrier. Not really the shape of the barrier that a real alpha particle tunnels through, but it's a problem we've done already, so you'll get a feel for how these things are done. So I'm imagining I've got an alpha particle, and I'm going to take the case of U-238, uranium-238, which emits an alpha particle of 4.20 MeV. And I'm going to imagine that the barrier that it has to penetrate looks like this square barrier that has a height V0 and a width A. Okay? And the question is, what height and what width should I be using? Imagining here that the alpha particle has to overcome what's called the Coulomb barrier. That is between an alpha particle, which in this case is thorium-234. Imagining that the thorium and the particle have to just be in physical contact. There are two spheres which are touching. And we'll see in a few days that go as a to the 1/3. There's a constant of about 1.4. And then it goes as a to the 1/3, where a is the sum of the number of neutrons and protons in the nucleus. And so the Coulomb barrier is just the electrostatic potential energy, if you like, when these two charged spheres are touching each other. And so that's the product of the charges Z1 and Z2 divided by the sum of the radii of those two spheres, and I'm saying that's a to the 1/3. So A1 is going to be 4, that's the alpha particle. A2 is going to be 234. And the Z's are the Z of the alpha particle, which is 2, and the Z of the thorium-234, which is 90. So when I plug that in, I get an approximate value for the height of that barrier of 23.2 MeV. And that's not too far off, okay? It's on the order of 20 MeV. The radius is another story, the distance over which. And you can say it's roughly the sum of the radii, okay? This is where it actually gets a little fuzzy. And this number is not terribly good, and we'll see why later on. And it's also true that the barrier does not have a rectangular shape. But if I take this barrier height and this barrier width and plug it into the formula we wrote down the other day as the particle going through a rectangular barrier, this is the expression. I just plug in those numbers, and what I find is the transmission probability is about 10 to the minus 29. And that should be somewhat reassuring, because classically there's no way in the world the alpha particle could make it through. It's only got 4.2 MeV, and the height of that barrier is 23 MeV. So classically the transmission probability, quantum mechanically it's not 0, but it's darn small. And what we're going to see when we treat this more precisely with a better estimate of both the shape, the height, and width of that barrier, we're going to find that this is actually a gross overestimate of the transmission probability. The real number is even smaller than. The point is, it's not 0. Okay, that's really the message I want you to take home, that the probability is not 0 and it's calculable. Okay, this is a very simple-minded way to do it. We'll see a more sophisticated way later on. But within we calculate it and get numbers which are of the right order of magnitude. Okay. The other day we started the discussion of angular momentum. I'm going to finish that up today. And remember that we've talked about two different kinds of angular momentum. One is the orbital angular momentum associated with moving with a linear momentum about some origin. And that's what we call L. And L is a vector. And L, it turns out, is quantized in units of h bar. H bar, 1 h bar, 2 h bar, and so on. And then in addition, there's a kind of angular momentum known as intrinsic spin, that these particles, the protons, the electrons, intrinsic angular momentum as well as the orbital part, and that we refer to as S, and S is also a vector. And then the total angular momentum, which we call J, is the vector sum of those two. And since neutrons and protons and electrons all have intrinsic spin of a half h bar, that means that J in magnitude is equal to either L plus a half or L minus a half. And the other day I had this wrong, so I tried to correct that here. That's the magnitude of the vector J. And so the example I showed you the other day is, suppose L equals 1. That is, I have an orbital angular momentum of 1 unit of h bar. And let's say this is a neutron. Then the possible values of J for that neutron are either L plus a half, which would be 3 halves, or L minus a half, which would be 1 half. Now, just again, so J is this vector sum. J has a magnitude. And the way we often talk about it is in terms of the magnitude of J squared, the square. And one of the weird things quantum mechanically is that the value of J squared is h bar squared times J plus 1. And this has to do with the fact that if you have a angular momentum, L or J, you can determine the magnitude of it and you can determine one component of it. That is, you can determine the length of J and you can determine J sub Z. You can't simultaneously measure J sub X and J sub Y. That's another reflection of the uncertainty principle. Okay? So J sub Z, you can, and this will also be quantized, okay? It will be quantized in half integer units of h bar. S sub Z is going to be a half an integer, L is going to be an integer. And if I have a certain value of J, given by the upper expression here, then J sub Z, the Z projection of that angular momentum, can take on 2J plus 1 separate values. So for example, if I have a particular value of J, the Z component of J can range from minus J to J in steps of 1 h bar. So if J, let's say J is a half, the lowest case we can have. Orbital angular momentum L equals 0, intrinsic spin a half, so J is a half. J sub z then can go from minus a half to plus a half, and it would only have two values. And just to verify that there are two J plus 1, in that example, J is a half. I multiply it by 2, I get 1, I add 1 to it. So there are two values of J sub z, plus a half and minus a half. If L equals 1, then I can have J equals 3 halves, or J equals 1 half. If J equals 3 halves, then I should have 2 times 3 halves, or 3 plus 1, 4 different possible J sub z values. And that can be minus 3 halves, minus a half, plus a half. So that's a general rule that for every value of J, you have J plus 1 magnetic substates, as it's often called. Okay. It gets a little worse with regard to quantum mechanics. But again, we have to face up to this. Because we're going to deal with systems where we have more than one particle. And we have to think about what happens to a wave function when I do have more than one particle. So if I have a system that has two particles, and let's assume they're identical. So imagine it's 2 protons, or 2 neutrons, or 2 electrons. As far as we know, every single electron is identical to every other electron, and same for protons and same for neutrons from another. So if that's true, then the wave function psi that describes that composite system of 2 particles, 2 identical particles, can be written as a product of 2 individual wave functions. So let's say I've got 2 neutrons. I write down the wave function for particle A, and I say that's psi of A, and I say that the particle is located at position R1, and then the other part So I interchange them, and I just If they're really identical particles, then there's no measurement of the wave function, which is the thing that I can actually use to calculate anything. That can't change. But the wave function itself, as I said before, is something we directly measure. So if psi squared but it makes an enormous difference in the way particles behave. So there are 2 kinds of particles in the universe that we know about. There's a kind of particle for which the wave function does not change itself. This is symmetric. In other words, I interchange the labels of the particles. The wave function doesn't change. That's symmetric. If the wave function does change sign under the interchange of the 2 identical particles, that's called antisymmetric. And it turns out the particles in the universe, one of which behaves symmetrically and one of which behaves antisymmetrically. So the class of particles for which the wave function does not change sign are particles that it turns out have integer intrinsic spins. Not the orbital part, not the J part, the intrinsic spin, little s. So these are particles that have 0s, 1s, 2s, and so on. And when I mean that, I mean in units of h bar. Those are called bosons, okay? And it turns out they obey what's called Bose-Einstein statistics. There's another kind of particle where the wave function does change sign. So when I interchange the 2 identical particles, the wave function changes sign. These are particles that have half integer spin. Does that mean half h bar? These are called fermions, okay? Now, the electrons, the neutrons, the protons have what intrinsic spin? A half h bar. So which kind of particle are they? Fermions. Okay. Boson that you know of. A photon, what's its spin? 1. A photon has spin 1. Okay? An example of a boson. And it turns out there are others as well. So, the The major classes are the bosons, the fermions. Photon has spin 1. A pion, which is a particle we'll talk a little bit about later, turns out also to be a boson. It has intrinsic. And then imagine all mediated masses, and they attract each other because they're spinning gravitons back and forth. Gravity. Photons are the particles which are exchanged between charged objects, and that's what's responsible for electricity and magnetism. And in an older version of the nuclear potential model, it was thought that it was pions that were being exchanged that account for the nuclear force. In any event, these are all bosons. They have spin 0, 1, and 2. Fermions, examples I showed you before, electron, proton, neutron, and there are others. Okay? Now, amazing things, and the reason it's these particles from one another is that they are subject to what's called the Pauli exclusion principle, which means no two fermions can have. Okay? This is only true for fermions. It means that I can only put one particle into one mechanical state. Okay? I can only put one electron or one neutron or one proton into one quantum mechanical state. If I want to make that system of two neutrons, let's say, I have to put them in two different quantum mechanical states. And so, assuming all other quantum numbers are the same, that would mean, for example, I can have a neutron sitting here in a state where its intrinsic spin is pointing up. I could not put another neutron in exactly that same state with its spin pointing up. I'd be forced to put it in with its spin pointing down. Okay, that would distinguish one from another. They would not be in exactly the same quantum mechanical state. And again, you think, well, who cares? But if you think about chemistry and what it is that distinguishes one chemical from another, it has to do with the way they're arranged in their orbits. The electrons are also fermions. They're the thing. And that's why you keep all the electrons in the lowest orbital, because it can only accommodate two electrons. One would spin up and one would spin down. If it weren't true, then all the electrons would chemistry. What's possible is this exclusion principle. And we'll use that later on when we're talking about the shell model to understand why it is we can only put a certain number of particles into a given quantum mechanical state. And it's this reason, that you can't have more than one particle with one set of quantum numbers. So far, we've been talking about these quantum mechanical states as though they live, that you prepare a system and it just sits there. And if that's all, that would be pretty boring. There would be active decay, there wouldn't be nuclear reactions, and so on. So now we're going to talk about a drawing like this, and you'll see these kind of drawings over again. And what I mean by this is you have some initial state labeled I, which in the way I've drawn it is at a higher energy than some other state labeled F, final. And so typically what happens is if you prepare the system in this higher lying state, it always likes to go to the lower state via whatever mechanisms that do it. Alpha decay, beta decay, gamma decay are all ways for the system to lower its energy, and nuclear reactions will turn out also be a way for the system to lower its energy. Energy state F. And what that means is that the system has a finite. What that means is, according to the uncertainty principle, that that state does not have a precisely defined energy. The uncertainty principle says that the product of the uncertainty in the energy and the uncertainty in the time is at least h bar over 2. And given that the state doesn't live forever, that sets a limit on how long you can sit there and watch and measure its energy. And that limit then establishes a limit on the energy with which you can define that state. So this state that's a measure of the uncertainty of the energy of that state. And the lifetime and the width are related to one another through the uncertainty principle. So the lifetime time, which we'll call tau, is h bar over gamma, where gamma is the width. And the decay probability, rate of decays, we call lambda, it's 1 over the lifetime. So at this point, remember is that states of finite lifetimes do not have precise energies. They have some width. The longer the lifetime, the broader they are in energy, the wider they are in energy. And the longer they live, the narrower they are. And it turns out, within the context of quantum mechanics, you can calculate the rate at which a state will decay. It's given by something called Fermi's golden rule, after Enrico Fermi. And don't worry about the details here. We'll use this a little bit later on when we talk about beta decay. But the basic idea is that there's some constants out front. There is a matrix element, which is a measure of how much the initial state and the final state look like each other. And there's an operator, V, that connects the initial state to the final state. In beta decay, it's a certain kind of operator that turns a neutron into a proton. In different types of radioactivity, a different type of operator. But the point is, you sandwich it between the initial and final states, you do that integral, and you multiply it by what's called the density of states, the number of final states there are within a certain energy of the final state value. And this is how you calculate the rate. So don't worry about the details of it. We'll come back when we talk about beta decay. Okay. Now, quantum mechanics is over. What we want to now start doing is talking about the phenomenon of radioactive decay. And again, the way Lilly does this is he creates it very fast. So I'm going to go over it a little more slowly and explain a few more points than he does, because we're going to come back and use this over and over again. So what we're imagining now is a system of atoms or nuclei that are radioactive, things that either undergo alpha, beta decay. And prepare a certain number of these particles, n. They're all identical, they're all created initially, and they're sitting there, and they're all radioactive. So if I have a system n of these radioactive particles, and they're all the same type, and I want to know how counter I did the other day for demonstration and bring them up there, measure them, what I'll find is there's a number n initially present, then the rate at which they're decaying, that is the change of n with respect to time, dn dt, is given by that very simple expression. It's equal to minus lambda n, okay? Where lambda is what's called the decay constant. This is a number. It has units of inverse time, 1 over time. Particular number for each radioactive isotope. Each isotope has a unique decay constant. And so the rate of decay of this system is proportional to how many of these atoms I've got sitting there, and the proportionality constant is what we call lambda. Don't know when they're born. They don't know when they're supposed to die. They don't. We found experimentally okay. It's as though atomic nuclei are totally divorced from the rest of the universe. So they don't know what the anything else about their environment. All they know is that there may be, cobalt-60, and they're supposed to decay with a 5-year half-life, or they are, some other isotope that has a different half-life. And experimentally, this has been tested to very high accuracy. So what that means is I can take that expression and integrate it. And I know that lambda is a constant. It doesn't depend on time or anything else. So I say I want to find a function such that when I take the first derivative of that function with respect to time, I get the original function back times a number. And the solution to that is an exponential. What that means is the number of these radioactive nuclei, which is present as a function of time, t, is just the initial number, whatever it was at t equals 0, times e to the minus lambda t, where lambda is that decay constant. Okay? That's the exponential decay law. And that's been many, thousands of times, from that. So we're going to spend a fair bit of time talking about radioactive systems and trying to understand how you can calculate decay present as a function of time. Now there are sort of extreme examples you can take, and I'm going to take one extreme right now, which is very, very long-lived nuclei. Okay, these are things like K, which we talked about the other day. This is a naturally occurring isotope that has a half-life of about 1 billion years. Lanthanum-138 lives 10 to the 11th years. This is something times 10 to the 10th years, and so on. These are all so long-lived that they're naturally occurring. I can dig up a piece of rock or dirt around, and I'll find these things there. So they've survived over the 4.5 billion years since the Earth formed, and they're still around today. And what that means is that over the time interval I'm going to measure, okay, which means minutes, hours, or maybe days if I'm really patient, those time scales are incredibly short compared to this half-life, the half-life of these guys. So what that means is that really very, very few of the nuclei that I measure will undergo decay. Radioactive nuclei are present simply by going and picking up a sample and weighing it. If I've done some chemistry and I know that my sample only has potassium in it, and I happen to know the isotopic abundance of potassium-40, then by weighing the sample, I've determined N. I take that sample and I stick it in front of my Geiger counter or whatever other decay device I'm going to use, and that measures for me dN dt, the rate of decay, and the ratio of dN life of isotope. Sort of counterintuitively, it's actually very easy to do. You might think I have to wait 1 billion years to watch half of the K40 to decay away, and of course, we can't do that. But in fact, it's very easy because this number is essentially a constant. This is a constant. The ratio is just the decay constant. So that's how the lifetimes or half-lives of isotopes are determined. Called natural radioactive decay. The age years. Bang, of course it's about 4.5 billion years, and these are examples of isotopes which are still around because their half-lives are long. Should look at these two for a second. We're going to 38, the most isotope of uranium, has a 4, which means that since the solar system formed, only about half of the U-238 initially present decayed away. On the other 5, which is the useful one for our purposes, meaning it's a better fuel for our nuclear reactors, it has a half-life of only 700 million years. Only. It's still a long time, but that's about, 7 half-lives since the... Actually, relatively little U-235 that was initially present has survived to today. So if we had waited a little longer in the big scheme of things to figure out how to make nuclear power work, there wouldn't be any U-235 around. If it had taken us another few years to figure out how to make nuclear power happen, we wouldn't have any fuel. On the other hand, it would have been easier if we'd figured it out a billion years ago when there was more U-235 around. And in fact, we're going to talk about this later, nature figured out how to do it all by herself 2 billion years ago. She made a nuclear reactor happen naturally, and the only reason it could happen is that 2 billion years ago there was more U-235 around, and it was easier to make that happen. This is a natural reactor that took place in Africa about 2 billion years ago. We'll talk about that. Okay. So these nuclei, the uranium and the thoriums, primarily decay by alpha emission, and they have long half-lives because those alpha particles are trying to tunnel through those quantum mechanical barriers, and they don't have classically enough energy to get through. And that's what makes these half-lives very long. It turns out the daughters, the nuclei that are produced as a result of those alpha decays, are also radioactive. They end up decaying by alpha and beta and gamma decay. And what eventually happens is the uranium and thorium decay eventually to stable nuclei of lead. 206, 207, 208 are the eventual decay products of uranium. And this gives rise to the ability to date the age of rocks based on looking at the atomic abundances of these things. So this is an example of what's called a decay series or a decay chain. This happens to be for the parent isotope thorium-232, so that's up here. And these boxes represent a different isotope. And so the thorium-232 I mentioned is one of these long-lived naturally occurring guys. Its half-life is 14 gigayears, 14 billion years. And the way it decays is by alpha emission. Alpha decays to radium-228, 0.7 for half-life. And by half-life, I mean the time it's required half of the nuclei initially present to decay. So for the thorium, it takes 14 billion years for half of them to decay. For the radium-228, it only takes 5.75 years. So the radium, it turns out, beta decays, and that's why the arrow's going in that direction here. So he beta decays into actinium-228, which has a 6.1 hour half-life. And you don't need to write all this down. I mean, this isn't the kind of stuff you need to know, but you need to understand how to analyze and make sense of alpha decay, which changes the Z of the nucleus by 2 units. It decreases the Z by 2 units. So thorium has a Z of 90, radium has a Z of 88, and then by 2 beta decays, you bring the Z of the nucleus back to 90. But the mass is 4 units lower because you've emitted it. You end up going from thorium-232 down to chains for U-235 and U-238, and you can look them up, okay? But the bottom line is that these long-lived guys eventually, by measuring the abundances of these stable isotopes, we can infer how long the rock's been sitting there accumulating these decay products. And this is the basis of radioactive dating. Okay. Very often, and those nuclei are examples, radioactive nuclei decay by more than one mechanism. So imagine I have some isotope, I call it Z0 and A0. So it's got Z0 protons in it and a total atomic mass of A0. And it can undergo 2 different kinds of radioactive decay. Maybe one is alpha and one is beta, for example. Let's call mode A, the one on the left is called decay mode A. And what happens then is that this initial isotope decays into a different isotope that I call Z. And V decays into a different isotope, Z sub B. So I can write down the rate of change of the parent isotope and let's alpha decay, the NDT sub A, is the number of the parent isotope there were, and times the decay or lambda A. And similarly, the rate for the beta decay, mode B, dNdt, is the number of parent isotopes times lambda B, the decay rate for mode B. Decay rates, and I can have more than 2 decay modes. I can have different decay modes, and I would just generalize this formula, keeping track of the decay rate for each individual decay mode. And we come up with the concept of a branching ratio, or the probability for one decay mode versus another. And so if the rate is called lambda t, then the branching ratio or the probability for a mode A is then lambda A divided by the total, and the decay rate or branching ratio for mode B is lambda B divided by lambda total. Now, very often we have a system like this shown here where it can decay by more than one mechanism, like I said, alpha decay or beta decay. But experimentally, for whatever reason, it might be easier to measure one decay or the other. Both. And very often what we're trying to do is measure the half-life of a radioactive system. And the formulas we write down tell you the number. And measuring the number of atoms is not usually an easy thing to do. And instead of that, what we measure is the number of decays that happen in a period of time and relate that using these expressions to calculate the half-life. As it turns out, it's easier to measure alpha decay than it is beta decay. And I measure the rate function of time. The question is, will I measure the true half-life of the isotope or not? And this always is a puzzle to people. Let me give you the answer and I'll try to motivate why. The answer is it doesn't matter which mode you measure. You always measure the same half-life. Even if one is a million times faster than the other, you always see the same half-life. And the analogy I like to use is, imagine you had a bucket of water. So this is my drawing. Decay by two different mechanisms, A and B. And the analogy I use here is I imagine I rate at which I could imagine combining the two holes into one, whose area is the same as the sum of those two, and watch the rate of the decay out of here, and again I'll get the same answer. Okay, so it doesn't matter which one you study. It seems counterintuitive, but in fact it's true. Okay, now if we're going to study radioactive systems, that means they don't live forever. That means very often I can't just go pick them up out of the ground and measure them. I have to make them. And the way we make them is some nuclear reaction or radioactive decay. And so we have is radioactive nuclei of species C are present as a function of time as I do my experiment. Certain rate So now I have a slightly more complicated differential equation that, okay, one of the homework problems except this is to take this solution and plug it into that equation and see that it solves it. Okay? So either way, you can start from first principles and do it, or you can just plug this in and show that it solves it. But the point is then that the number is a function of time, number of species C is a function of time, is R, the production rate, divided by lambda, the decay constant, times 1 minus e to the minus. Grows. So, actually, let me skip down here. So, draw what that solution looks like. This is it. So this is the number of species C present as a function of time, and it's being measured in units of half-lives here. And so at short times, what happens is the number grows more or less linearly, but eventually the decays start becoming more and more important as the number of them grow. And so the curve deviates from a straight line, and if I wait long enough, the number becomes a constant. Okay? Get into what's called equilibrium, where the rate of production equals the rate of destruction. Eventually, this term goes to 0 as t gets very, very big. And so this whole term cancels out, and I end up that the number as a function of time just becomes a constant r. If I ask myself, what is the rate of decay then, that's lambda n. So I would multiply. Which means the number does not change with time. Actually, have a constant number. It doesn't mean nothing's happening. It means that I'm producing at the same rate they're decaying. This is an extreme I mentioned earlier where I have a very, very long-lived isotope. So lambda is small. I can expand that exponential, and under those circumstances, find that RT is just a constant, and the number just grows linearly with time. On the other hand, for a very long time for something where the half-life is not so short, not so long rather, and then I get into this situation with the destruction rate, and that's when I get into my secular equilibrium. Another case we often have is a system where we have a radioactive nucleus decaying into another nucleus which is also radioactive. And it decays into something which is stable radioactive. And this is what's called the granddaughter. And the decay chain I showed you a little while ago, many generations of daughters down, going from thorium all the way down to lead. To these function of time. And only have the parent present, and then the daughters grow and decay as a result of the decay of and I just watch how these numbers evolve with time. So what that means is that at time 0, the number of species 1 present I'll call N0, and the number of species 2 and 3, meaning the daughters and granddaughters, are 0. So then I know how to calculate the rate at which species 1 changes with time. dN dt is just minus lambda n. It's just decaying. There's no. And I know that the answer to that is just going to be the exponential decay law that we saw a minute ago. On the other hand, it's being produced as a result of the decay of species 1, but it's also decaying. And the rates for the production not necessarily equal. So species 2 rate of change of abundance is equal to plus lambda 1 n1. It's the rate at which species 1 is decaying into it. And then it's being destroyed by its own decay, so minus lambda 2 n. You can take this expression for n1, plug it into here, and then solve for n2. The minus lambda t's. And as you go down the chain, these expressions get more and more complicated, but the principle is the same. You solve them one step at a time. So to get n3, I'll have an expression that involves the decay of n2, and if it turns out n3 is radioactive, then the decay of n3, and I'll get a messier expression, and I can solve terms in it. They're known as the Bateman equations, and you can look them up if you like. And a nice this, which turns out to be very important in nuclear medicine, is this system shown here. So technetium-99 is a radioactive species that lives about 6 hours. It emits a nuclear gamma ray, which is often used for medical imaging. So people get injected with this stuff, and then we use detectors to measure where the stuff is in your body to learn about various bodily functions. That half-life is so short that it's able to transport the technetium. In fact, most of the technetium we use in this country is actually made in Canada and shipped over here. And so the way it's shipped is as the parent isotope, which is molybdenum-99, which has about a 2.5-day half-life. So it's easier to try to it's then it decays away with a 65-hour half-life, and over a period of time, the technetium-99 reach a maximum in the amount of technetium-99 there, and that's kind of what's being shown here. So the curve labeled N sub A, in this case, would represent the molybdenum-99. It's going to decay away with its 65-hour half-life. The technetium-99, the daughter, starts out with 0 abundance because there wasn't any. It grows with time and eventually reaches a maximum and then decays away. And the granddaughter, ruthenium-99, is stable, so it just keeps growing with time. So these equations turn out to be important for practical. If you want to know how much time it's going to take to get the technetium to a usable form and with enough activity. Okay. So I'm going to stop here for today. That's enough to get started on the homework. And then on Wednesday, we'll finish up the rest of the discussion of radioactive decay. So why don't we take a break now for about 10 minutes. Problems, they're due now. Thank you.